The next unit discusses the theoretical foundations of the discrete element method.
Welcome to this chapter on the theoretical background, and we will start with an overview of what you will learn in this unit. First of all, we will learn about Newton's law applied to a two-particle or a binary particle collision. Second, we would like to discuss two different approaches used in DEM-type simulations. So the discrete element method can essentially be split up into two rough categories. Next, it's important for you to be able to realize that a collision in the soft sphere DEM method that we will discuss has a certain duration, and it's of key importance to know about this duration. Contact detection is the next topic. It is very important because it is decisive for the computational efficiency of the DEM. So before we start with the discussion of the theory, I would like to comment on why we need theory. Well, the theoretical framework behind a numerical method, and the discrete element method is nothing else as a numerical method, is very important to understand the application bounds of a method, right? And the specific theory we need for the DEM is the Newton's law, or Newton's laws, as we will see. And you see a nice schematic illustration here. So this was Mr. Newton sitting below an apple tree, and then this famous apple fell on him, or on his head. And from that observations, he essentially postulated three laws. The first law, and this is the modern interpretation of the first law, is that there is an infinite large number of inertial observers. So it doesn't really matter which of these observers we pick, we can always see the same physics behind it. We'll use explicitly the first law. It's more modern interpretation, it's more the general idea behind everything that has to do with Newton's laws. What we will use is Newton's second law, and this says that the change of translational momentum, and this is the original form from Mr. Newton, is proportional to the applied force. So P here is a translational momentum. This is a time derivative. The momentum, the translational momentum, is the product of the mass of a body, or a mass of multiple bodies, a mass of the system we'll look at, you will see that later, multiplied with v, which is the velocity. Please note that scalar quantities are always here indicated with italic letters, and the bold non-italic letters are vectors, right? So v is a vector and m is a scalar quantity here. Again, this is the time derivative, and this is the equal sign. This is then Newton's law, the sum of all forces. So we will deal with forces that act on our bodies. For the nomenclature, I would like to refer you to the separate nomenclature document. You don't have to look it up, and it will not be explained every time we discuss equations. Just please look it up in the nomenclature. Important, there's also the rotational analog to this equation that you may have learned already in high school, which says that the change of the rotational momentum, capital L here, is a vector again, which is the rotational momentum, is proportional to the sum of all torques, in this case acting on the body. Please note that we are free to choose the system boundaries. So we can pick one particle here, m is here the particle mass, or we can also pick multiple particles, then the mass would be here the mass of both particles. We will see later that in the case of rotation, we have to be a little bit careful about the definition of the rotational momentum here, because it depends on the origin that we pick. Please also note that both equations here, the translational momentum equation and the rotational momentum equation, must be satisfied separately. So both must be satisfied, and it's not enough that only this equation is satisfied. No, both must be satisfied. An important third law is actio et reactio. This is known as Newton's third law, and it simply tells that each action force also has a reaction force as a consequence. We will see that explicitly later. That is it already with the theoretical foundation. There is nothing more to say. Of course, the force laws have more theory behind, but we will talk about this later. Let us now illustrate these Newton's laws, so the second and the third law. And for that, I would like to let two particles collide in a binary collision. The first particle, the red one here, is located here at this position, so at x minus 1, so x is minus 1, and y is 0.2. The units here are in meters, but it really doesn't matter. We always recommend to use SI units, but you could also use alternative ones if you like, right? And the second particle here is located at this position, at the origin, 0, 0 position. Both particles have, of course, a radius r. It's the same for both particles. That's why the mass is also the same. We have chosen this density. We have a moment of inertia that is dependent on the shape of the particles and the distribution of the mass inside the particle. If we assume spherical particles, solid spherical particles, we know that. You can look it up in the nomenclature. Particle 1 is moving with a velocity of 5 meters per second in the x direction and 0 meters per second in the y direction. We have no initial rotational speed of both particles. Both are at rest. Particle 2 is at rest, has no rotational speed. Particle 1 also has no rotational speed, but please be reminded that the rotational momentum or angular momentum has to be defined relative to the origin. And this is important. It's for this particle because it doesn't start at the origin. It is shifted by 0.2 meters in the y direction. It has a non-zero angular momentum. It can be calculated like this. For particle 1, this would be 0, but we would have here this cross product of position and velocity is non-zero. Let us now look at the results of a DEM simulation considering this setup. I forgot to note that in what we're going to do now in this simulation, we will exclude gravity. There is no gravitational force. The only force we will allow is the contact force, which will be introduced later. So let's have a look at the DEM simulation. Again, particles start in this configuration. Particle 2 has 0 velocity, both translational and rotational. Particle 1 has a translational velocity. So you see the particles will approach each other. Particle 2 will change its velocity, it will increase, it will have an increased momentum, translational momentum. And particle 1, the momentum of particle 1 will be decreased. If you look closer, you will see that there are these gray points, and these gray points are also vectors illustrating the rotational speed of the particles. So the reason why you don't see them as vectors in this plane is that they are pointing outside of the plane. They are normal to the plane we are watching, okay? But you see that they grow in size if you look closely. So again, let's watch the movie. Initially, this angular momentum points are 0, and then when the collision starts, it grows in size, okay? Beautiful. So let us now look at the situation after the collision. We have seen that velocities have changed of both particles and that particle 1 has now a velocity v1, we denote it as v1, and an angular velocity omega 1. So the angular velocity has obviously increased. We see that it's going to be negative, a negative valued angular velocity in the z direction. And particle 2 has also picked up velocity, and the angular speed will be also in this direction, also negatively oriented. Here for completeness also the nomenclature that we have used for particle 2, velocity v2 and angular velocity omega 2. This is it for this part, and next we're gonna look at binary particle collision analysis. So how can we explain what we have simulated here?